We're back here today with 7.3 linear functions. Once again, this is coming from the 8th grade book, so this is primarily for the honors kids. Um, Linear functions, again, the example problems don't seem to be working so hot, so we're going to go ahead, dig into 7.3 homework, and probably looking at about 5 questions I'm going to shoot to you or talk to you about. Again, we have talked about this before. We didn't refer to it as functions, we refer to it as linear equations. So it says we're going to graph the set of ordered pairs and determine whether or not it represents a linear function. So if I take a look at 1 comma 4, and again, you might have to blow these things up with the magnifying glass a little bit, but 1 comma 4, 2 comma 7, so you can see this one would be out. 1 comma 4, 2 comma 7, you can see this one will be out because I don't have a 1 comma 4. I'm at 1 comma 7 here, so that one's out, so it doesn't look like it takes a whole lot to see that we're at 1 comma 4. Let's take a look at this one in a little bit larger fashion. So you can see here that we're at 1 comma 4, 1 comma 4, 2 comma 7, 3 comma 10, 4 comma 13, and then 5 comma 16. So D is going to be our correct answer in this particular situation. All right, so they're going to ask you, it appears as though on part 1 the focal point is we're going to give you a graph. When we give you a graph, can you identify the graph for the given points, and is it a function or is it not a function? And when I say function, I mean a linear function. And so yes, this is a linear function because if you connected those dots, then obviously it would create a line, a straight line. Moving on to my next question. It says we're going to take a look at a graph of this once more. So they also might refer to this as rate of change. Okay, if we're talking about rate of change, then you need to be thinking of y over x, which again, we've talked about this countless times. That's the constant of proportionality. That's the slope. That's the unit rate, just to name a couple synonyms, if you will, for rate of change. So if we take a look at this, the graph is given to you, and we could look at this and say, does this represent, it does represent a linear function. What is the rate of change? So if we took just 2 of these points, and again, all we have to do is take 2 because they're already telling us it's a linear function. So if we took the difference in y values, 8 minus 5, over the difference in the x values, which is 2 minus 1, we can see that our rate of change is simply 3 over 1, which is 3, which tells us that the slope is 3, the constant of proportionality is 3, etc., etc. Okay, move on to my next problem. Right here. And on my next example, what do we got? We've got determine whether the relationship is defined represents a linear function or not. All right, so what we're going to do is we're going to take a look at the gaps here. And so it's easy to figure out that the gaps between all these are 1. Okay, so we know that the y values are going to be 1. What about over here? This is 2, this is 2, this is 2, and this is 2. So in each of these instances, we have a rise over run of 2 over 1, a rate of change of 2 over 1. Okay, so we do believe that the rate of change is constant and the rate of change is 2. So my answer should be C. Answer should be C here. All right. Moving on to question number 4. And on question number 4, once again, determine whether it's defined in this situation. So once again, we notice this is 2, 2, 2. Over here we're at 8, 8, 8, 8. So it appears as though my rate of change is 8 over 2, and it's constantly at 8 over 2, which is going to be 4. Okay? So yes, because the rate of change is 4 is what we think the answer is, and that is correct. All right, so again, these are things that we've, and this is kind of why we're moving through this chapter so fast, we have kind of talked about this, just not using these specific terms in terms of using the term function. Completing homework assignments. We have the time is in minutes and the number of problems left. What's the rate of change of this linear function? So they're already telling you it's a linear function. And obviously, if they're telling you it's a linear function, then you know that the slope's going to be the same. So really all you'd have to do is take a look at just two of these and say, hey, it looks like it's, 10 minus 7. And then it's 4 minus 5, which is going to be 3 over negative 1. All right, so that means that my rate of change is going to be negative 3. Why is it negative 3? Because they're paying attention to, as time moves along, how many problems are left. And so that's why it's going to be negative 3 as opposed to positive 3. And so then they're going to turn around and make sure that you understand, what is this negative 3? What does the negative really mean? It simply means every minute the student has how many fewer problems. Because it's got a negative sign, that's the word fewer in essence. So you have 3 fewer problems every single minute in that situation. We move on to my last example, which is going to be problem number 6. On problem number 6, as we take a look at it, we've got, again, construction worker, the amount of cement in a cement truck every 5 minutes as it empties. What's the rate of change for the volume? So how long until the volume of the cement in the truck is 45 cubic feet? So if we take a look at this, we could identify with the fact that we have 115 minus 80, and we have 15 minus 20. So if we looked at that, that would be what? 35 over negative 5. And so if we have 35 over negative 5, we're looking at what? Negative 7, representing the rate of change here. Negative 7. Okay. And then the question is, the volume of the cement in the truck is 45 cubic feet after how many minutes? 45 cubic feet after how many minutes? So knowing that you're going to lose 7 every minute, okay, you could use that information. A couple different ways you could get here. Eventually, we're going to want you to think about this from an equational standpoint, I believe. But in this situation, we could say, all right, if I lose 7 at 21 minutes, I'm going to be at 73. At 22 minutes, I'm going to drop another 7, so I'm at 67. At 23 minutes, I'm going to drop another 7, so I'm at 60. At 24 minutes, I'm going to drop another 7, so I'm at 53. Hey, subtracting those right? No. This is 66. Stupid hit. 66, 59, 52. And at 25 minutes, I'd be at my 45. All right, so it looks like 25 minutes is my answer in that particular situation. Boom. Okay. Now, I'm not sure they're going to show this to you, and I'm going to go ahead and think about this, so I might be looking ahead here a little bit. We could look at this and say, all right, wait a sec. What is we're at y equals negative 7 is our slope times x. At x being 0, we're at 220. So this should be able to turn out when we want 45 as the volume, so that'd be mine. Remember, this is x and this is y. When we want this to be 45, we should be able to plug this into this equation. We were able to come up with the equation. I'm going to subtract 220 from both sides. And when I subtract 220 from both sides, might want to grab your calculator here if you feel like it. 45 minus 220 is negative 175 equals negative 7x. And then at this point, what am I going to do? I'm going to divide both sides by negative 7. And when I divide both sides by -7, x turns out to be 25, all right? Which is exactly what we said the answer was right there. So we obviously want you to be able to do it with a table, but long story short, we'd like to see you eventually get it to be able to pop it into an equation, all right? All right, that should do it then for 7-3. All right, guys. Hey, I'm back here with 7-4 from the 8th grade edition. We're on nonlinear functions. This one's going to be pretty short and sweet, I think. Once again, we'll go straight up to the homework to speed the process up, potentially. Again, feel free to ask me any questions that you have via email. Love to hear from you, see if you have anything going on. Again, this is silly. Determine whether each function is linear or nonlinear just from its graph. The function of the first one, obviously, is nonlinear, seeing as though it's not a straight line. We'll check that. Second one, obviously, is linear because it is a straight line. So it's that simple on, probably you're going to get 4 problems or so that look very similar to that. We're going to skip problem 2 because it's very similar to it. Take a look at number 3. It says Justin opens a savings account with $6 and saves 4 every week. As soon as it says he saves 4 every week, boom, that's really all you need to know that this is going to be a linear situation. You could verify this by taking a look at gaps. Obviously, if we look at the gaps on the x values, the gaps on the x values are simply 1. And if you look at the gaps, since he's doing $4 a week, the gaps are going to be, he's going to add $4 every single week. So that means our y value, our y over x, our COP, our slope, our unit rate, our rise over run, is going to be 4 over 1. It's going to be constant. And if that slope is constant, then yes, you have a linear function. Okay. Moving on to my next question, number 4. Again, very similar situation. All right, so I don't see any need to jump all over that. You're going to be looking at gaps, and if the gaps, if the y over x, the constant proportionality is constant, then between each of those x and y values, then you've got a linear equation. Spend a little bit of time here on the next piece. Once again, you're really going to get a chart here, and again, they give you a vertical chart in this situation. So obviously, it looks as if over here on our x values, if I look at it from a y over x perspective, we've got a gap of 1. So that holds true with what we saw in the previous 2 examples. But take a look here. We've got a gap of 5. We've got a gap of 7. We've got a gap of 9. We've got a gap of 11. These gaps continue to go up. And because of that, because this does not stay constant, this is going to represent a nonlinear function. Okay, a nonlinear function. And again, you could verify this by graphing these points. If you graph these points and then you try to connect them, you're going to find out, quite frankly, they're not going to create a straight line. And if they don't create a straight line, then they obviously cannot be linear. All right? Take a look at number 6. Very similar situation. They're using some bigger numbers. Again, the one thing you got to be a little bit careful of is these are gaps of 1 because we're going by the year. Here we have gaps of 400, then 800, then 1600. So in essence, they're doubling, all right? And first inclination might be, hey, that's going to be linear, but if they're doubling every single time, every single year, oops, I screwed it up. That's going to be a nonlinear situation, all right? In fact, that's kind of what's going on right now with the whole coronavirus thing, with everything's not a linear situation. We get the same number of cases every single day, all right? And then the last piece that they're going to want you to know is they're going to want you to know how this works with a graph. And so if I take a look which function or functions are linear and which ones are nonlinear, realistically, if we take a look at number 1, it appears as though this guy is linear because it's a straight line. This guy is not a straight line. This guy is a straight line. So it looks as if, 1 and 3 appear to be linear functions. Scratch that baby out. Is there a second part of this? I believe there is. What do they want on the second part? Select each function that is nonlinear. All right, I'm not going to insult your intelligence. We're going to go ahead and mark that. And I think that should do it. We shouldn't have too much difficulty, I wouldn't think, on section 4 here. All right? Okay, have a great day, and we'll see you when we see you.